Hello, everyone. So today I'll be presenting homework 5. So we will be talking about the definition of diffusion, the importance of diffusion. I will explain the process of the diffusion. We will talk also about the denoising diffusion implicit models, classifier free guidance, latent DDPM, and the performance matrix, FID, IS, precision, and recall. So imagine that you had a pure image and you started adding noise gradually until you ended up with the random noisy image. What if you can do this process in reverse and you start from an image with random noise and we start removing the noise gradually until you end up with pure image. This is the diffusion model. Why is it important? First of all, a diffusion model produces high quality output, so it has like exceptional generation of images, audio, and it's more consistent in training compared to models like GANs. So we have two processes in the diffusion model, the forward process and the reverse process. So for the forward process, uh, we add the noise over t time steps. And this process, which is denoted by Q, takes the form of Markov change, where the distribution at a particular time steps only depends on the sample from the immediate previous step. However, the reverse process is the denoising part, where the model learns to gradually remove the noise from data at each step. And this is for the aim to reconstruct the original image or the data from its noisy version. And actually, the main goal of training a diffusion model is learning the reverse process, which is specifically training the p theta x t minus 1 given the xt. So how do we add noise? So actually, the Gaussian noise, the noise added in diffusion models follow the Gaussian distribution, which means at each diffusion step, we inject some random noise that has this familiar bell curve distribution. And the sampling is the standard normal sampling, where we sample the noise from a standard normal distribution, which has a mean of 0 and variance of 1. And our training objective, so how do we train this model? We train it using the MSE, the mean squared error loss, between the predicted noise, the model's predicted noise, and the actual noise, which is added during the forward process. So as you can see, here's the loss function. So first, this is the expectation over the noise variable, the epsilon, the initial data points, which is the x0, and the t time steps. Also, the epsilon theta is the model's predicted noise at time t. Also, the square root alpha t scales down the original data by factor of the theta t square root, reducing its contribution as the t increases. And also the square root 1 minus alpha t scales up the noise component, making it more dominant as the t increases. And this is also what the squared Euclidean norm, which measures the difference between the actual noise epsilon and the predicted noise epsilon theta. Now for the algorithm, so we start with a sample from our data set, which could be an image, audio, and we add some noise to it, and then you pass the noise image into your model, and then you predict the noise that was added, and then you try to minimize the distance between that and the actual noise, and you keep repeating this process until the model converges. So for the sampling, imagine that like if you want to synthesize a new sample, like an image, let's say, you can start with a random noise, and then you pass the noisy image into your model, then you predict some noise from that, and you can subtract this predicted noise from the actual noisy image, hoping to get the denoise image back instead. So what is the denoising diffusion implicit models? So there's some limitations in the DDPM inference. So actually the DDPM inference follows a sequential denoising. So the process, so it must process each time step in reverse to remove the Gaussian noise. And this happens due to the nature of the Markov chain of the reverse process. So in the DDPM, the inference step involves the random sampling to reverse the diffusion process. So here is the denoising function. So this term represents the mean calculated by the model at time step t, which is the prediction of the clean data if no noise was added at step t. And the noise schedule represent the standard deviation, or actually the noise level at time step t, as defined by the noise schedule of the diffusion model. And actually, it also determines how much noise was likely added at this step. And here the epsilon theta is the estimated noise. So this is the model's estimation of the noise that was added also at time step t. And this estimate is subtracted from the ZT, which is the noise sample, which is a random noise sampled from a Gaussian distribution, which is typical in stochastic processes. But here definitely it's used in a controlled way for refining the estimation. So in the DDIM, we replace the random sampling with deterministic sampling. So the DDIM uses a non-Markovian process, allowing for fewer time steps, where it modifies the inference step by modifying the reverse process, making this process deterministic. So here the predicted x0 represent the next step prediction of the clean data, adjusting the current data xt by removing the scaled estimated noise. And the direction to xt adjusts for the noise direction, helping to fine-tune the trajectory back to less noisy data. And here is the random noise, which is added to introduce the variability, ensuring that the model captures the full data distribution and maintains the generative diversity. So now, what is the classifier-free guidance? So as we saw earlier in these previous methods, that they are still incapable of generating an image for a given class. So what if I provided the class name or textual description? Can I control this process? Yes, this could be controlled using the classifier-free guidance, which allows for targeted generation of images by conditioning on a specific class label. So here is the algorithm. So we train a classifier on both the original and the noisy versions of images to predict class labels. And then the gradient of the classifier's prediction is calculated and scaled and also added to the diffusion model's output to steer this image generation toward the desired class. Now, for the latent DDPM. So why do we need a latent space in diffusion models? First reason, and one of the most important reasons, is the efficiency. So actually, running diffusion models directly in pixel space is computationally very expensive. So LDMs, they operate in compressed latent space, which reduces the computational cost and complexity. So in the data compression process, the LDMs capture the essential features of the dimensional uh, data like images in a more compact and a structured form, enhancing processing efficiency. So and this also, we get improved performance because working in the latent space focuses on the relevant aspects of the data, improving both the efficiency and the effectiveness of the generation process. So for the latent DDPM, so as you can see here, so first it maps the data into latent space using the VAE or any other similar approach. So the encoder compresses the input data into a latent representation, and then the decoder reconstructs the original data from the latent representation. And for the model evaluation, uh, uh, we evaluate the performance of our model using different matrix. So we use the FID, where we measure the distance between the feature vector of the real and the generated images. So whenever the score of the FID, the lower, the better. So this indicates that we are producing um, a good image, better image quality, and similarity to real images. And the IS assesses and assesses the diversity and the clarity of the generated images using pre-trained models. So the higher the scores, this denotes that the better the image clarity and variety. Also, we use the precision and the recall to evaluate the quality and the diversity of these generated images. So high precision indicates realistic images, while high recall shows variety close to the actual data set. All of these matrix are found in the PyTorch using the PyTorch matrix. Now I will go through the code